I already know they're going to do well, you know? Andy?
So when, like as a student, when you're in Cal 1, everyone talks about like how hard Cal 2 is. Like, what's the opinion of Cal 3?
Cal 3, I hear varying things. I'm teaching this semester, I'm so excited. I'm teaching Cal 1, Cal 2, and Cal 3, so I'm pretty pumped about this semester. My opinion of Cal 3 is that you've suffered, like now you know what suffering is, right? You've been through Cal 2. So like you have a new idea of what it means to be in a math class. You know, like your bar's moved now.
So it's like the same amount of suffering, but since you suffered before, you don't.
Exactly. I think Cal 2 is like, Cal 2 and Cal 3 is about the same. Cal 3, what makes Cal 3 hard is that Cal 3 is just so dense. The amount of material in that class is just mind-boggling. Difficulty-wise, it's integration and differentiation. It's the two things, Cal 1 and Cal 2, just go into higher dimensional space. We're going into three-dimensional, four-dimensional, five-dimensional space. And so, but there's no like Cal 1, it's all about differentiation. Cal 2 is all about antiderivatives or integration, sequences and series. Cal 3, there's not like this new thing, this third thing. It's Cal 1 and Cal 2, but now we move into higher dimensional space, which means we need vectors, which means we need to kind of reformulate the way we do things because now we need vectors instead of just points. And so I think it's the same challenge, just for you it will seem not as bad because nothing increased. That's my opinion. Okay, well, let's get down to business. We want to chat more, we can. The way the course is laid out, the way I have this laid out, is that we're going to start in 3.5, and then we're going to go to 3.6. And these sections are, we're not quite yet getting into Cal 2. All right, we're still doing Cal 1 stuff right now. We're taking derivatives. We just need to make sure that we understand how to take derivatives of certain functions that perhaps you did not see in Cal 1. And I don't know, everyone is coming from a different place. I know for my Cal 1 students, we did do 3.5, but we did not do 3.6. So we're going to start with 3.5. We ready? Here we go. So 3.5, there's a bunch of notes in here. I'm not going to get into all these notes because we don't need them all to do what we're about to do. This is more of a reminder. Okay, 3.5 is about inverse trigonometric functions. The camera will get from about here to about the same distance on the other side. I'll try and stay on camera for everything, except things like this where you don't necessarily need it. Remember that from pre-cal, right, there's 6 trig functions, right? Cosecant, secant, cotangent. We have our 6 trig functions from pre-cal, and then each of those have derivatives, which we learn in Cal 1, right? The derivative of sine is cosine x, derivative of cosine x is negative sine x tangent, secant squared x. Those 3 you should know. That you should not be looking at anything. That should be right there. Okay, the next 3 you may not know, but let's see if anyone does. Derivative of
Secant tangent?
That's the derivative of secant. Okay, derivative of secant x is secant x tangent x. This one is negative cosecant x cotangent x. And this one is negative cosecant squared x. This one's secant squared. Okay, these 3, they're on your formula sheets. These 3 should be in your head. All right, so we have 6 trig functions, right, from pre-cal. Each of those have six derivatives, right? We have 6 derivatives there. All right. Then in pre-cal, we learn that there are 6 inverse trig functions, right? The functions that undo those functions. And that's what the first part of these notes are about. Like, what does it mean to be a one-to-one function? Okay, here are the trig functions. They're not one-to-one because they fail the vertical line test. So we do domain restrictions. It's all pre-cal. That's why I'm not going through this heavily. We do a domain restriction. Once we do a domain restriction, then we can define the inverse sine function. It has certain restrictions on it, right? Then we can do the same thing for cosine, right? We can take the cosine function, we can restrict it, and then it again, would have an inverse. Okay, so I'm going to just jot down over here. We have for each of these functions, we have an inverse function. You can either write arc or you can do the -1. I'm going to do the -1. Quick show of hands. How many of you remember, at least at some point in pre-cal, having covered those 6 trig functions? Everyone remember seeing those? No? Yes? Raise your hand. I just want to make sure. Yes? Everyone, because look, the analogy is a train, right? Train station. You get on that train, you go to your next destination, right? If you miss the train in this class and it goes, it's over. Okay? Like you have to hold on, all right? Yeah, hold on. Everyone hold on. We're going, all right? When I ask questions, if you're unsure about something, if you're unclear, right? This is your education. I don't want you to miss the train. Okay? You've got to be willing to stop me and ask questions, all right? Raise your hand and I'll be happy to address. If it's something that we need to take outside of class, we will. Yes?
So what are the 3 that are supposed to be in your head?
First 3. Derivative of these first 3.
Yeah. What are they again?
What are they? Derivative of sine x is cosine x. Derivative of, these are on your formula sheets. Yeah, they're right here. I'll just tell you where they are. Reference page 5. Formulas 13, 14, and 15. And then the other 3 are right below it. See it? But those 3 should be automatic. Like you should be to the point where you are comfortable with that. So if you're not, memorize it. Have that done by next class. These are the 6 inverse trig functions. And each of those should have derivatives, shouldn't they? So what are they? Well, spoiler, they're right here. Okay, look at your formula sheets. Numbers 19, 20, 21, 22, 23, 24. See those? Those are the derivatives of the 6 inverse trig functions. So what I'm going to do right now is I'm going to prove to you formula number 19. I'm going to prove to you that that's true. So if y equals the inverse sine function, I want us to show, or let's do it this way, not show. Let's just say find y prime. Now you already know the answer, don't you? Formula 19, you know the answer. But where did that come from? The reason I'm going to show this to you is because what I do while I'm showing you this, what I'm about to do, is something we're going to need in a week or two. It's a technique that's very useful when we're doing something called trigonometric substitution, which is coming down the road later, right? So that's why I'm showing this to you right now, is because of something that's going to come up later. All right, so I'm trying to find this. Ready? What's the derivative of this? I don't know formula 19. Is that a question? No? I thought I saw you raising your hand. I'm sorry. Okay, so I don't know other than formula 19. That's cheating though. So what I'm going to do is this. I'm going to start this by looking at what I do know, and that is I could take that equation, y equals sine inverse x, and I could take sine on both sides. Now, the reason I'm doing that is because I know that if I take sine and inverse sine and I put them together, compose them, right, they should kill each other off. That's what inverse functions do, yes? Now, why I'm doing this, just hang tight. All right, you'll see why I'm doing this in a minute. Put these two together, they kill each other off, and that leaves you just with x, right? So sine of y equals x is where I am. Now remember, what I want here is y prime, right? I want the derivative of this. I want the derivative of y. So I'm looking at this, and I'm like, well, I've switched over to this. Now what I'm going to do is, back in Cal 1, something called implicit differentiation. Implicit differentiation. I'm putting it there in case you need to go back and look it up. What I'm going to do is I'm going to differentiate both sides of the equation with respect to some variable. And in this case, I'm going to do it with respect to x. So I'm going to take the derivative with respect to x on the left, and then the derivative with respect to x on the right. Look familiar? That, like, is my notation look kind of familiar to you? No? All right, let's start with the right-hand side because it's easier. What's the derivative of x with respect to x? Remember my Cal 1 students, me telling you all that story about the club, right? Yeah. It's all about with respect to what variable, right? So the derivative of x with respect to x is just 1, right? So this is 1 on the right-hand side. Let me continue right here. So I have equals 1, okay? That's the right-hand side. This is the tricky one. What's the derivative of sine of y with respect to x?
Is it cosine y with y here?
Yes, it's cosine y. So the first thing you're doing is you're taking derivative of sine of something, right? Derivative sine of something, we said earlier, was cosine of it. So cosine of y times, now the chain rule, you take derivative of what's in the sine function. And what's derivative of y with respect to x? dy dx. But dy dx is actually what I'm trying to find here, right? dy dx is actually what y prime is by definition. So all I need to do now is divide both sides by cosine y. And I will isolate the dy dx. Was your winter break too good? Are you okay? You're trying to like pull this stuff out of the darkness. 1 over cosine y. That's the answer. But wait a minute, that's not what the formula says, right? So I've screwed up first day. Something's wrong. Look at this. This has y in it, doesn't it? What does your answer have in it? X. Okay, so the problem here is that I have found the derivative, but I have found the derivative with respect to the variable y, where this was the original thing, right? Right here? It said y is some function of x. So I'm going to take derivative of that. Shouldn't the answer also be in terms of x? Right now, it's in terms of y. So all I need to do is somehow get this back to something with x's instead of y's, right? So here's what I'm going to do. I'm going to leave that right there. That's the important part right there. I'm going to go back to when I did this step right here. That right there. I'm going to go back to that. And I'm going to use that information to create, this is the part that's going to come up big for us later, something called a reference triangle. A reference triangle. So what a reference triangle is just a triangle that helps you visualize a relationship that you have. This right here is a relationship I have. Sine of the angle y is equal to x, right? Sine of some angle y is equal to x. When you're studying in pre-cal, sine, right, when you think about, remember the SOHCAHTOA thing? Sine on a right triangle is which side over which side? Opposite over hypotenuse. So what I'm going to do is, from this, I'm going to draw a right triangle. I'm going to make the angle here y because I'm doing sine of y. The angle here is the thing that's inside the sine function, y. And then this x, I'm going to rewrite the x as x over 1 so that I create a ratio. And then I'm going to look at that as being x being the opposite side and then the 1 being the hypotenuse, right? So this is going to be the opposite side, hypotenuse. And I'm going to draw that on my triangle, opposite, hypotenuse. All we're doing here is visualizing that relationship, right? That relationship has that as a visual connection, yes? Now, why did I do this? Because I want to know what cosine of y is, right? And I know what sine of y is, don't I? So to find cosine of y, I can use this triangle. Cosine, by definition, is which side over which side? Adjacent over hypotenuse. Do I know the adjacent side?
Yeah.
Indirectly, I do, right? It's not like explicitly in front of me, but I can solve for this side because I have two sides of the right triangle. I can always solve for the third. Yeah? So let's call that side, I don't know, let's call it A. Let's call it A for adjacent, I guess, or A for A squared plus B squared is C squared, however you want to look at it. This becomes A squared plus X squared equals 1 squared. And then subtract square the 1, you get 1. Subtract X squared on both sides. And then finally take the square root. And when I take the square root on that, when I take the square root, I'm supposed to do plus or minus. But A here is the side of a triangle, so I'm going to just take the positive answer. Okay? Now, based on this triangle, what is cosine of y?
Adjacent over hypotenuse.
Adjacent over hypotenuse, so it's just this over 1, isn't it? So I can write from here, I hate having to force myself in this small space, but we can make it happen. So I'm at this point right now where I can say that cosine of y is this over 1, which is just itself, like that, right? That's what cosine of y is. And now I come back over here where I had the derivative, right? And I say, okay, my derivative is 1 over cosine y, which is square root of 1 minus x squared. And that right there should be the formula 19 that you see, right? Okay. So let's set up another one. I'm gonna see if we, actually we might go through the whole thing. I think it's first day. Let's see if we can do another one of these, all right? Because this whole like method and technique I think is important to see. Any questions on this before I erase it? We're going to do another one, so we're okay? Let's do the inverse tangent derivative. So if y equals tangent inverse of x, I want us to find the derivative. So if this said just tangent, right, not tangent inverse, if that was just tangent, the derivative is secant squared, right, from Cal 1. So I'm trying to find the derivative of the inverse. So I don't know what it is. Well, I could cheat, right? I could look at the formulas, but I'm not going to. I'm going to follow the same procedure I just did before. I'm going to take this equation. Here's my answer. I'm going to take the equation. What do you think I'm going to do first? Take tangent on both sides, right? And that will allow me to kill off this inverse tangent. So take tangent on both sides, tangent y equals, I'll go ahead and write it, tangent of inverse tangent. Then I'll have tangent y equals what? X, right? The tangent and the inverse tangent go away. That's the whole point of doing that. Is to kill off that inverse tangent, make it go away.
Multiplying inverse by itself.
It's not multiplication. I mean, I know what you're saying. This looks like multiplication. It's composition. Okay. You're taking tangent inverse and plugging it into the tangent function. So it's actually a function plugging into another function, which is composition, as opposed to multiplication, where you're multiplying two things together.
Multiply 5 times 0.5, you get 1.
It's like this. If you start out with an x here, you send it through the function tangent inverse, right? Then it comes out here as tangent inverse x, right? Whatever it is, it's some number. This is some number, I'm going to call it y. Now, if I take that y and I want to send it back to x, what I would do is I would take that and I would plug it into what function? To tangent, right? Tangent would take it back. So if I do tangent of that, it would go back to x. And that's exactly what we're doing here. X first goes into the tangent inverse function, comes out over here. And then what we do is we take that and we send that answer back through the tangent function. and it comes back out as x. That's not multiplication. So I just want to be clear. It looks like multiplication, but it's not.
That's with any inverse function.
That's with any inverse function. Yeah, I mean, I could have just arbitrarily replaced this with f inverse, and this would always work the same way.
So it's like plugging it into a calculator. It's not multiplication. But
It's college algebra. It's college algebra composition. F of g of x, Fogg and Goff. Do you remember that from college algebra? It's that same concept.
So, yeah, it's 1 to 1.
All right, what now?
Tan y over x.
What am I doing? Implicit differentiation. I'm going to differentiate both sides of this equation with respect to x. So the derivative on the left side with respect to x, tangent y, and then the derivative with respect to x of x. The right-hand side is 1. The left-hand side, you have to just be careful here because it's tangent of y, and you're differentiating with respect to x, so you've got chain rule here. So what is derivative tangent of something? Secant squared y, right? Secant squared y times, now the derivative of y, dy dx. I can't imagine the trauma in your mind right now if you don't remember chain rule. Like if you don't remember implicit, I understand. So you might have to get refreshed on this, you know, if you're like, hey, you know, I took Cal 1 a year ago. You know what I mean? But this is where I expect you to be day one here, this sort of thing. So if not, get caught up, come get help. We'll get you up to speed if we can. All right, now what? Triangle, yep. Yeah, let's divide by secant squared y. Dy dx equals 1 over secant squared y. And just to be clear, everybody, this is the same as 1 over cosine squared y. Isn't it? Because secant is the reciprocal of cosine. So if I say secant squared, that's the same as saying 1 over cosine squared. And then I could do 1 over a fraction and flip everything. So isn't this all just cosine squared y? I'm just pointing that out. We didn't need that. But I mean, that's the sort of algebra we need to, like, should be comfortable with. All right, that's where we are, yes? Now the triangle, and what am I going to base the triangle on? What equation in here am I going to use to create my reference triangle? Which one? Tangent y equals x. That one right there. That's the one. So time for my reference triangle. Here's a triangle. What am I going to use for the angle in here? Y, right? Because that's the angle that's being plugged in tangent y. Tangent, by definition, I'm going to rewrite the x as x over 1 again. Tangent, by definition, is SOHCAHTOA, opposite over adjacent. So this is opposite over adjacent. So I'm going to label this x, and I'm going to label that 1. And I need to know what cosine is, right? I need to know what cosine is, cosine of y, and then I need to square that answer. So cosine, by definition, is adjacent over hypotenuse, but I don't have the hypotenuse yet, do I? So I'm going to solve for the hypotenuse. So I'm going to call this h. I don't know what h is. Let's put that right here. Anytime I start getting kind of upset with myself that I'm having to cram all Cal 2 onto this small thing to put it on a video, I think of Isaac Newton sitting in his shed creating calculus by himself, and I think like we can do this. We can get around this, right? I mean, basically that's what Newton did. I mean, he basically went to school, learned all the math that was known at that point, and then went home and worked in his shed in his backyard and came up with calculus on his own. So I think we can handle this, yes? A squared plus b squared is c squared. Create the relationship. Pythagorean, right? That's just Pythagorean. And we're solving for what here? H. So I can just take square root right now. Square root on left side, 1 plus x squared equals h. Hey, wait a minute. I thought the square root of 1 plus x squared was just 1 plus x. I thought you could just take the square root of each one. No? Yes? No? No? Yeah. Why not?
Because there's like an operation between the two.
Yeah, you have addition between the two. If you have addition or subtraction, you cannot take the square root of each one. If it was multiplication or division or something, you could. That's not right. That's not correct. I'm a little off topic, okay? But when this sort of thing happens, you can always convince yourself of something like this by just taking something like this. If you think that's true, just try that, right? You think that this means square root of each one, so this should be 1 plus what? 2, which is 3. That's what you're saying to me? But what's 1 plus 4? 5. Square root of 5 is 3? I don't think so. So you did something wrong here. Look, when I was a student, okay? When I was a student, I wasn't like completely confident in my math. That's the type of thing I would do to like when I was unsure. I'd be like, oh, I can't do that, you know? Until I got to the point where I was comfortable with it, right? Which, by the way, didn't happen until I started tutoring in the math lab. That's when that's when all the algebra came together for me. When you're forced to show someone else, so for any of you who are STEM majors and you're trying to get better at math, go throw yourself in a tutoring lab. That'll get your math pretty tight. Okay, I'm way off here. So that's my h, right? That goes here. And now I'm ready for my answer. Here it was, cosine squared y. So what was cosine y? Adjacent over hypotenuse, cosine? So adjacent on that triangle is 1 over the hypotenuse. Do you all agree that that's cosine of y?
Yeah.
But I need to square it. So I square that. And when you square a fraction, you square the top and bottom. So square the top, 1 squared is 1. Square the bottom, and the square root goes away. And that should be what's on your formula sheet. Yes?
Why were we solving for h again?
Because we wanted to know, this right here means cosine of y squared, right? That's what we had here. And I wanted to make this have x's in it, not y's. So I said, okay, well, wait a minute. I need to figure out what cosine of y is first, right? So I go to my triangle. Cosine is adjacent over hypotenuse. And we didn't know what hypotenuse, right? We only knew these two. So to figure out hypotenuse, I needed to call it hypotenuse and solve for it. Any other questions? Yes.
How would you write this out?
Oh, hold on. Yes.
So, I'm a little lost at that point as well. I don't really understand it. So, like the part that like I understand is when we find the derivative. Of,
Yeah.
We find y prime that's cosine squared of y, and then we're trying to convert that y into the x.
Yes.
Like, could you kind of just skim over that? Like after that, I'm a little bit lost.
Like, why are we doing it? Or like you're okay that we need to go from y to x?
How do I make that y an x?
You need to find, the thing is right here, cosine of y, we need to somehow figure out what this is in terms of x.
Yeah.
The only thing that we have that connects y and x together, the only thing we have is that, right? That connects y and x together. It's a trig function with y and then x. That we started with this.
Yeah.
So what we're going to do is use this to draw a picture. And then from that picture, once I have two sides of a right triangle, I can always get the third. And now, once I have that triangle, I can look at it. I can say what's sine of y, cosine y, tangent y, secant y, cotangent. I could find any trig function in terms of y now, couldn't I? And I wanted cosine of y. So now I'm just going to use that and that, adjacent hypotenuse. So I'm using the one connection I have between y and x to be able to figure out what that is in terms of x. What that is in terms of x.
Okay. Do you think Isaac Newton had to invent SOHCAHTOA, or was that already math at the time?
I have no idea. Yeah.
How would you write out the final answer in like a pretty format?
You would write, well, it depends. You could probably do this. Tangent inverse x, right? The derivative of that is 1 over 1 plus x squared. And that's what we just showed, right? I should also point out, it doesn't matter if the 1's in front, you could switch the order, put x squared plus 1, right? It's addition's commutative, so I think it appears that way in most formula sheets, though. So I've shown what the derivative of 2 of the inverse functions are, right? There are 6 inverse functions. They all have their own derivatives, and they're all on this sheet. I'm not going to prove the rest of them. You should know they're here, okay? You should know that they're here. All right, now, 1204. What we want to do now is say, okay, we've got 6 new derivatives, right? We have 6 new derivatives. We've got them, they're on our formula sheets, we're happy. Well, I don't know if we're happy, but we know they're there, right? And now what we get to do is make sure we know how to incorporate these with all the other stuff we learned in Cal 1, which is product rule, quotient rule, chain rule. Okay, so these are our new derivatives. Let's make sure we can differentiate. So let's start with this one. There's an example here. Let's find the derivative of x squared sine inverse of x. Find that derivative. So you're Cal 1, right? You passed Cal 1. I want to differentiate that. Cal 1, you have product rule, quotient rule, chain rule, right? So what rule am I going to use here? Product. Everyone see it? Everyone see the product there? You have multiplication happening right there. Now, we're going to have a little bit of an issue here. A lot of you have learned the product rule this way. If you have some function times another function, that when you differentiate this product, I don't even know how you learned it probably. What? That's the way you learned it?
Yeah.
That's good.
Oh, I was worried.
You said you learned it, the derivative of the first one, that would be that, times the second one, plus the derivative of the second one times the first one. That's the way I teach it. Perfect. If you learned it that way, that's excellent.
What would be the other way?
I don't know. Do you know it another way?
I mean, I always thought of it as
Who learned it? G prime times F plus F prime times G? It's the same thing, but it's doing the derivative on that one first, no? Or change the order here? You learned F times G prime plus G times F prime. Okay, that's the way it's, I think, taught in a lot of books. This one right here.
I think there's another way you can probably write it.
Yeah, I mean, you could keep flipping things and moving
I
things.
just thought I just put a plus sign between the two and then the derivatives on the outsides.
So there's different ways we could write the product rule, right? But let's write the quotient rule. If you have division, what's that formula? Derivative of the top, which is f prime, times the